Good evening friends, welcome. This is the live session 2 for the course on energy conservation and waste heat recovery. My name is Anandaroop Bhattacharya. You have probably seen enough of me and probably tired of my face. So, I am here today to answer your questions, and if you have any comments, suggestions, advice for or inputs for improvement, those are also extremely welcome. Okay? Only then can we become better at what we do, only through feedback from you. Okay? I hope you have liked and enjoyed this course so far and at least learned something new. Okay? The topic of energy conservation as well as waste heat recovery and even energy storage, which was covered in the second half of the course, these are all very, very pertinent and important topics as of today. So, whereas what we have taught in as part of this course from the P.K. Das and I, these are probably a beginner's course, I would say, just to introduce you to these topics. Each of these topics, there are hundreds of researchers who are probably spending their whole careers on them. Okay? So, definitely the whole aim of this course was to, number one, give you the or basically convey the importance of the topics, overall topic that we are talking about, and number two, probably inculcate some interest, and if so, maybe some of you can pursue any one or more of these topics as part of your professional career or as part of your future activities. Okay. So, with that, what I will do is I will first start with some of the questions that you people had raised in the forum. Okay. And thereafter, probably we will take up questions that you are asking on the live session or something that you have uploaded. I did not see till maybe till about half an hour back, there was no question on the Google spreadsheet, but hopefully you will have some live during the session. So, let me start with some of the questions that you raised on the forum. The first one was that I have was about movement of holes. This is during the thermoelectric generators, and there was a question as to how do the holes move. Okay. Now, I want to make sure one thing, if I did not mention it during the course, my mistake, but holes are not physical entities. Okay. Hole is a concept. Hole is envisioned as, let us say, it's an atom or a molecule where the outer shell could have had one or more electrons to make it stable, but it does not. So, it is an acceptor. It is there is space to accept an electron. Okay. So, then the question is, if hole is just a concept, then how does it move? Okay. So, let me try to explain this in this way. Let us consider that I will just illustrate this using 5 atoms like this. The first one is a hole in the sense that there is space to accept additional electron. I am sorry, what happened? Okay. And the other 4, they have electrons. So, let us say this is time 0. Then the tendency is for this electron to jump and move to the neighboring atom where there is space, or the atom which is able to accept an electron. So, at time 1 we may find the configuration to have changed like this. And then an electron from here may try to jump to the next one, time 2. At tau 2, what do we have therefore? We will have a configuration like this. Time 3, similar, because here this electron will try to move, okay, and so on. Now, look at this picture. Where was the hole at time 0? Over here. And where is it now? Here. So, the hole has you can say the hole has progressed from the left to right, but essentially it is not the hole that has moved, it is the electron which has jumped to those to a place where it can be accepted. Okay. So, this is what is meant by movement of holes. Okay. So, I hope that answers your question, and in thermoelectric generator that is how it is essentially movement of electrons, and but in the p type when we say movement of holes, it is through jumping of electrons. Okay. And the rest of it probably there is from the lecture you will be able to understand. Also there is an YouTube link from a lecture by Anastasia, which I had put as part of the in the slides. So, please go through that as well. She also mentions what a hole is, and just that it is a fictitious, it is a hypothetical concept. Okay. It is not a physical entity, it is the absence of an electron which we want to imagine as a hole, and then the current movement, since it is opposite to the direction of flow of electrons, we like to imagine it to be current flowing in the direction of holes. Okay. All right, I hope that answers your question. The next one is, there was a question as to why in the pressure drop equation for a heat pipe, the question was that why was I adding, the question is why are we adding change in pressure PV, change in pressure PV, which is the vapor pressure in the above equation, since PC is the pressure that will be provided by the wick material. No. So, let me try to explain this here. Okay, I have drawn it horizontally, so that we can for the moment we can neglect the effect of gravity. Okay. So, this is my wick and this is the core. So, now what happens here? See, the liquid, and let us say this is my hot junction evaporator and this is my condenser. All right. So, what is happening is, oops, I am sorry, I do not know why this is coming here. Okay. So, what is happening is the liquid, when it boils, so there is a little bit of a technical error. So, I will just redraw this again. With the smart board there was probably some mistake that I was doing. So, let me try this again. Okay. So, this is the heat pipe and that is the wick. So, when I am heating it from this side, and then, so this is my evaporator section and this is my condenser section. So, if you consider the liquid or the fluid flow, for example, what is happening? Let us just consider this. So, this is the vapor and then this is condensed liquid. So, if you take this entire passage or the flow path, then what happens? You have a pressure drop due to the vapor, you have a pressure drop due to the flow of liquid through the wick, and depending on the orientation, which at this point should not matter, but depending on the orientation, you will also have a pressure drop due to gravity. These are all losses, except gravity, which can also be a gain depending on whether the evaporator is higher or the condenser is higher, but otherwise these are all pressure losses. Okay. So, I have to overcome this pressure loss. So, what is going to be the mechanism by which I am going to have that pressure head, so that I can overcome all these flow resistances which leads to these pressure drops. So, this must be less than or equal to my capillary pumping pressure. Okay. So, think of this as a pump and these as flow resistances in the path. If I have to give an electrical analogy, think of this as a battery and these three as resistances in series. Okay. So, I hope that kind of explains why the vapor pressure is also vapor pressure drop due to vapor flow through the core is added, because that is a loss, that is a pressure loss. Okay. It may be negligible compared to the liquid one, but still we have to consider that. Okay. The third question was, what is the meaning of passive heat exchange in case of a thermosiphon? A thermosiphon, if you look at it, the flow of the fluid happens due to density difference. So, it is passive because you are not using additional or external energy like operating a pump or a compressor or a fan to move the gas or the liquid. Okay. So, that is why it is called passive. All right. Then the next question was, again this is due to the during thermoelectric generation. It is said that half of Qj will be entering the module. Can you explain why half of Qj is entering? No. So, Qj here is the joule heat. Okay. Now, the joule heat is going to be generated uniformly as the current flows to the P and N junctions. Okay. So, therefore, during the energy balance, what we do is we assume that half of it is generated at the hot junction and half of it is generated in the cold junction. Okay. So, and that is probably, that is a very reasonable assumption given the symmetric arrangement of a thermoelectric module, a thermoelectric generator module or even a cooler module. The joule heating, I believe it is a reasonably good assumption or it is reasonably good to assume that the joule heat is generated equally at the cold and the hot junctions. That is why half of Qj is added as a generation term to both the to both the hot and cold junctions. Okay. Next was, why can't we burn solid waste in a boiler furnace like coal, so that we can achieve both burning of solid waste as well as utilization of burned solids waste heat energy. Okay. So, it is possible, but the reason why incinerator is used also has environmental implications. Okay. Incinerator, typically you just cannot take waste and burn it. We have to be very conscious about what are the gases that are released during this combustion, and these gases should not just escape to the atmosphere and pollute it or have any or pose any environmental hazard. So, that is why incinerator is used. Otherwise, there also it is burnt. So, it is also kind of there is a heat, it is burnt and therefore, energy is generated. Okay. The other thing is why it is not coal is typically the calorific value of such organic waste or solid waste is not as high as that of coal, but by all means any material that has high calorific value can always be burnt in a furnace, provided that the exhaust gases are controlled properly, emissions are controlled properly. Okay. Okay, this is about the year round air conditioning. So, what the question is, can the valve automatically reverse the refrigerant flow? Well, what I showed was a schematic. Okay. So, the valve, what it does is, after through the compressor, of course, the flow of the refrigerant is not going to be reversed. The compressor cannot keep compressing if if the entry and exit points are reversed. So, that is not the point. Okay. So, what happens is, when the refrigerant comes out of the compressor, it is depending on whether it is summer or winter, it is directed towards the heat exchanger either in the external ambient or inside the room. So, for example, in winter the compressed refrigerant vapor will come to the heat exchanger that is inside the room, whereas in summer it should go to the external heat exchanger. Okay. So, what I showed in the schematic was it was just a schematic representation. In pressurized water storage during peak hours, if the high pressure steam and water mixture enters peak turbine, do not it get damaged and corroded, because the dryness fraction of steam in accumulator is very low. Okay. So, what happens is there is a bit of expansion before it enters the peaking turbine, but it is correct that the peaking turbine materials have to be chosen such that or I would take it back and say that yes, there is a possibility of corrosion, and so therefore, the choice of pressure, temperature and the materials in the peaking turbine has to be judiciously selected. Okay. Pressurized water storage system, the example that was worked out, I believe you have the solution already. Our TA Manoj has already shared it with you on the forum. Okay, will NTU effectiveness method charts and formula be provided during exams? If it is required, it will be provided. No, you do not have to remember. The only simple formula that you are expected to remember, if at all required, is for a case where there is a phase change. So, either in the hot or cold fluid, there is no change in temperature. There the expression is very simple, and that I believe you should remember. But otherwise, none of the charts or the big formula you do not need to memorize. Okay. Okay. Lecture 64, the present value of installation, why salvage value is added. Why is salvage value added during the calculation of the present value of an installation? It is added because salvage value is a cash inflow. Okay. When you sell it at the end of its life, it is a cash inflow, and to let us say you sell something for 10 crores after 20 years of operation. Okay. So, today what I have to do is that 10 crores has to be divided by the discount rate to the power 20, which is the life cycle or the lifespan of the installation, but that value has to be added. That is the value today. Okay. So, why do I make something? I mean, if I have to run a business, if I have to make a plant and then run it, it has to be profitable. So, where is the profit going to come from? The profit. So, when I start it, I have spent money. Okay. So, that is a loss, but then the expectation is over the lifespan I am going to recover not just what I have invested, but a lot more, and not just in absolute terms, but in terms of time value as well, and that is why the present value of all the returns throughout the span or throughout the lifespan of the installation must be more than what I am spending today. Okay. And whatever I am going to earn from this installation, salvage value is also part of that. Okay. So, therefore, it has to be added. It is a cash inflow. It is a return on my investment at the end of its life. Okay. I think that is all we had from the forum, and now I think there are some questions from the live session. Can you elaborate principle behind material behavior with high electrical conductivity and low thermal conductivity simultaneously? Okay. All right. So, if you recall, what is Seebeck coefficient, or basically for thermoelectric generator or thermoelectric, whether it is cooler or generator, the Z value was proportional. So, the Z value was proportional to the electrical conductivity and inversely proportional to the thermal conductivity. Okay. So, therefore, in order to increase the Z value, I need to have a material with high electrical conductivity and low thermal conductivity. Unfortunately, most materials that we have do not, I mean, they go hand in hand. I mean, any good electrical conductor is also most generically a good thermal conductor as well. So, therefore, that is where the challenge was. Now, what happened was, with the advent of nanotechnology and the ability to grow thermoelectrics at nanoscale, this was possible. How? See, electric current, why does it happen? Because of flow of electrons, and thermal conductivity, especially for semiconductors and all, that happens because partly due to electrons, but also largely due to the lattice vibrations, which is also called phonons. Okay. Now, the mean free path of vibration of electrons is much smaller than that of phonons. Okay. So, therefore, what happens is, when we were able to grow these crystals at nanoscale, the length scale of these devices or of these crystals were such that they were larger than the mean free path of electrons. So, that electrons could pass through, the vibrate and pass through, but the phonons which has larger mean free path of vibration got blocked because it did not have the space to vibrate. Okay. So, as a result what happened was the electrical conductivity remained unchanged, it did not go up, it was what it was. Okay. It was not impacted, but thermal conductivity went down because the lattice vibrations could not take place, and as a result therefore, the ratio sigma over k shot up and Z shot up. Okay. All right. Is the present value of installation formula why salvage value is added instead of, can you please explain with a practical example? Okay. Sure. So, let us say today I buy a car, okay, and the car costs me today, my car which is my initial investment, the car is let us say 5 lakhs. Okay. Now, I am, this is a practical example, but again I am going to make it a little impractical in the sense that I am not going to add my maintenance costs, my insurance, all that stuff. Okay. Those are cash outflows. Just assume that I have bought a car and it runs. Okay. And because I have the car, I do not have to travel by bus, I do not have to hire a, when I go from Kharagpur to Kolkata, I do not have to hire a taxi, I can just drive my car. Okay. So, every year I say that every year I save 1 lakh on transportation cost. Okay. There is a little bit of exaggeration, but okay. Let us say I save 1 lakh because I make so many trips. Yes, I have to buy fuel and all, but that cost is much less compared to what I have to pay to a travel agent or pay to a driver and so on and so forth. So, therefore, my total I travel a lot, and therefore, every year by driving my own car I am saving 1 lakh compared to what I would have spent had I been using had I been using hired cars. Okay. So, therefore, every year this 1 lakh you can imagine is coming back to you. Okay. So, therefore, I can say that what is my cash inflow? Every year cash inflow CF1 equals to CF2 equals to CF3 equals to dot 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 CF10, and let us say I am driving this car for 10 years, after that the car is no longer drivable, and these are all 1 lakh. Okay. Now, at the end of 10 year my salvage value, I can sell the car for 2 lakhs. Okay. So, what is my present value? What is the present value? Value as in how has this car added value to my finances? Okay. So, present value of the car will be 1 lakh in the first year, but let us say there is inflation of 5%. So, 1.05 in the second year. So, till the 10th year this is what it is going to be, and then at the 10th year I am also getting 2 lakhs. These are all cash inflows. Okay. I do not think the last part is coming on the screen. So, I will just scratch it off and write it in the next line. This is my salvage value. I get this back. So, every year I will get back 1 lakh to my purse, and at the end of the 10th year I will get an additional 2 lakhs by selling this car. So, therefore, net present value will be the present value minus my investment. So, if I add all this up, this will be more than 5 lakhs, okay. And if I subtract that 5 lakhs, that is my net present value today. And then you have to, I have to make this call that, okay, is it a worthwhile investment, okay. Is the time, is the value that I get over the entire lifespan, including the salvage value, including the value that I get by selling it at the end of its life, is it more than what I am spending today when normalized over time, okay. All right. You can also look at it, I said I save 1 lakh, you can also think from the point of view of a travel agent. He says I buy a car for 5 lakhs and every year my net earning by renting this car will be 1 lakh, okay. And then the same calculations, and then again at the end of 10 years I will trade this car or whatever, I will sell this car off and get 2 lakhs more. So, it is the same formulation for him as well, okay. Is that clear? I hope it is. Explain Carnot's cycle. Or are you trying to say it is Carnot cycle? If it is Carnot cycle, then it is part of the first part of the course, Professor P.K. Das. So, I will have him, it is not proper for me to explain because he has taught it in a certain manner. So, I request you to post this on the forum and I will have Professor P.K. Das answer your question, okay. And I can answer, but then you will get inconsistent message, I do not want that to happen. How can we calculate enthalpies in the exam? Will we be given steam tables? Wherever you need enthalpies, you will be given, okay. Except in very simple cases where H2 minus H1 is just Cp delta T or things like that, sensible heating, etc. In that case, please keep that in mind, that you are expected to know, but otherwise wherever you need enthalpy values, it will be given to you. Okay. Any other questions on the forum? Okay. I hope I have been able to answer your queries to your satisfaction, but again if I have not, please feel free to raise these questions again on the forum and please let me know where which part you did not understand, and I will try my best to explain that again. Okay. I hope, I think I understand that your exams are next week. All I want to let you know is, please do not take too much of stress about the exam. If you have followed the lectures properly and if you have understood the materials, exam should not be a problem. Okay. The exams are typically in 3 sections. The first part will be simple questions of and then slightly more detailed in the second section, and the third one will be the most detailed ones. Okay. Okay, there is one more question. Heat pipe, can we assume liquid as water? Water is the most common liquid that is, or the fluid that is being used in heat pipes today, but that being said, there are heat pipes with other liquids as well. But if you are asking from the exam point of view, whatever is the fluid will be given to you along with its properties. So, you do not have to assume anything, it will be stated. Okay. All right. So, exams, all I want to say is do not take too much of stress, you will be fine, and but more if you have understood, if you have learnt and understood the concepts well, then it should not be a problem at all. Okay. So, please relax, focus more on the concepts and understanding, and then you should be fine. Okay. If your understanding is clear, it should not be a problem. Okay, I think there is one more question. I see it coming up. Can you explain how much energy can conserve in energy conservation and waste heat recovery in a plant? Well, that really depends, but typically they say that almost sometimes 30 to 50%. I mean the modern power plants are better at that, but in some of the older ones 30 to 50% of the heat that is rejected can probably be put back to good use. Okay. I mean 30 to 50% cannot be put back, of course whatever you are using there will be some efficiency in terms of recovery of that waste heat, but there is scope for using that waste heat, the waste heat that is otherwise rejected to the environment. Okay. So, any hot surfaces, for example, hot liquids that are flowing, the hot gases that are being go to the atmosphere, steam, etc. These are all sources from where we can recover. These are all what are potential waste heat recovery options from where we can generate some energy. Okay. Explain how bleed steam radiating system works. I am probably not understanding this question. If it was part of the second half of the course, week 7 onwards, I do not recall if I had taught this, or was it in the first part of the course, in which case again my recommendation would be to post this on the forum, and I will request Professor P. K. Das to answer the question. Bleed steam radiating system, I do not think I have taught this. Okay. Would you please still something about pinch analysis? Again, it is Professor P. K. Das's part. I do not want to jump in here. My suggestion is to again post it on the forum, and I will request Professor P. K. D to answer that. Okay. How important is this course for chemical engineering? Oh, a lot, because if you are in the process industry, definitely a lot of these are important. If you think of even in the energy storage part, chemical energy storage, I mean today when we talk about energy storage, it is primarily batteries and fuel cells, and these are both largely chemical industry. Okay. So, yes, it is extremely pertinent, and even the first half heat exchanger networks, or even any of these cycles, the combined cycle probably is power plant, more of power plant, but even Kalina, organic waste, organic Rankine cycle, these are all part of, these are equally pertinent in the chemical industry as well. So, I would say extremely important. Combined heat and power as well, okay, which I covered. These are all very, very important. Are there any major projects for final year students that final year students can do on heat pipe applications? Oh, yeah. Heat pipe in terms of applications, for example, let us assume that heat pipe is an extremely efficient conductor of heat. Okay. Now, think about it. I have shown some problems. I have shown some applications of heat pipes, including defrosting of or de-icing of roads. Okay. So, these are all very, very pertinent. Heat pipes are today used for hotspot cooling. Every laptop probably that you use today have heat pipes in them. Okay. So, I mean in terms of projects and all, yeah, I mean wherever you have some localized hotspots where you want to bring down the temperature, but however you cannot at that point because it is at some internal point or so, you can use a heat pipe to route that heat out to the place where now probably you can blow air on the other end and use it as condenser. Okay. So, heat pipes have lot of applications, and if you want to do a final year project and all, yeah, you take up any cooling application and it will help you, or any place where you need to uniformalize the temperature. And you think about it, for example, you use this is, by the way, this is not there in the market today, but any place where you have localized hotspots, for example, the chassis of your tablet, okay, can you use a heat pipe there? Okay. Think about it, I am not saying this is an application probably, but very thin heat pipes, flattened thin heat pipes of less than sub-millimeters and all is possible, is available today. Okay. If you extend heat pipes to vapor chambers, which is 2D flattened structures, even more. Okay. So, I think there are lots of options to do projects on heat pipes. Can you explain Carnot cycle? I can, but again this is first part, I do not know. Carnot cycle is something very basic and any basic thermodynamics book will have that. So, I am not sure exactly what you are looking at. I mean Carnot cycle, if I draw a TS diagram, this looks like this. So, there is a heat sink at T c, there is a hot at T h, and here you get work out and here you get work in. So, 2 isentropes and 2 isotherms, and beyond this I do not know really what you are looking for. Where was this? Can you explain difference between dew point and bubble point? I do not think this is part of the course. Okay. So, this is not part of this course, this is an external, this is an additional question. So, this is outside the scope of this course. Okay, there is one more question, where regenerative and reheat cycles both are used. Yeah, there are, if you just in power plants both regeneration and reheat are used. If you open any basic thermodynamics book, you will be able to see these cycles. Okay, even Sengel and Bowles, Moran, Shapiro, Pekenag, they all have examples with reheat and regeneration. Okay. Now, are there actual practical installations with both reheat and regeneration? I am not sure, but I would think there are. Okay. And again, this is from the first part of the course. Please, Professor P. K. Das probably will be able to give you a better answer. Raoult's law is also not part of this course. It is part of it's mixtures, thermodynamics of mixtures, but not part of this course. Raoult's law, in waste heat recovery, where will you use? Yeah, if you are looking at vapor absorption refrigeration cycle and you want to do thermodynamic analysis, Raoult's law does come into picture, but again outside the scope of this course. I teach another course on advanced refrigeration cycles where I teach that, but not as part of this waste heat recovery course. Okay, I am trying to see if there are many more questions. Okay, one more. Okay, explain the concept of OTEC power plant, ocean thermal energy conversion. So, if you look at the ocean or a sea, there is a temperature gradient at the surface and at a certain depth below. So, this temperature difference is not much. But if you think about it, this water, the volume of the fluid or the sea water is large. So, therefore, can this temperature difference be utilized to generate some power? Okay. So, this temperature difference between the surface and the depth, can it be used? So, that is the whole idea of ocean thermal energy conversion. So, here what happens is the temperature gradient along the depth of the sea water is being used to generate work. Material balance energy calculations. I do not know what is material balance energy calculations. I do not think this is part of this course. So, I am sorry, I do not have an answer. How important is this course? I would think it is important, otherwise I would not be, we would not be offering this course. So, I think the concepts that have been covered in this course are important. Now, whether it will be important in your career depends on what you want to do or what you are doing. Can you explain heat balance? It is a very generic term. I do not know what you call by what is heat balance. What we do is we do energy balance, which is first law of thermodynamics. Okay. So, the total, if you take a system, then the total amount of heat input and work input has to be equal to the heat rejected plus the work done by the system. So, thermal energy in plus work done on the system should be equal to thermal energy out plus work done by the system. Okay. And this work can be of different changes, different types, and this is what it is. And the other thing that comes into picture is, if there is energy storage inside, then you also have to add energy storage to the right hand side. So, whatever comes in is equal to whatever is rejected plus whatever is stored, okay, which can result in change in internal energy and so on and so forth. So, this is basic first law of thermodynamics. Is there any new advancement or innovative technology in waste heat recovery? Kindly share. I think there are new innovations, there are innovations that are being worked out. Some of them I am sure some of them are groundbreaking, but many of them are incremental advances to what is already being known. So, kindly share. So, I can give you an example. So, this is when I used to work for GE, General Electric. So, we were working on low cost waste heat recovery and we were working on organic Rankine cycle. And one of the pilot plants that was set up was in the unit where certain multinational company which has one of its establishments in North India, and they make potato chips. And what we found was they were every day rejecting about several tons per hour of steam at low temperature steam, around 150 degrees or less. And we wanted to, and we told them that, at this rate it is possible to generate a decent amount of electricity using organic Rankine cycle. So, that is where we started. Now, organic Rankine cycle, that way is known, but the innovations came in terms of components. For example, are you going to use a turbine? This is low cost again, the cost is very important. Are you going to use a turbine? Okay. And so, what we ended up doing was we used something called a screw expander. Okay. So, if you just do a Google search, you will know what is screw expander. It is not a turbine. You probably know what is screw compressor, and just the reverse of that is screw expander. Okay. So, screw expander is much cheaper compared to turbines, okay, or compared to a turbine of an equivalent size and capacity. So, that was the innovation, but of course, screw expander cannot handle very high temperature and pressure steam, I mean the more economic ones. Okay. So, but that was an innovation that came in, and then a lot of these at the component levels, what kind of pump to use, is there a better heat exchanger. So, all these are becoming important. Okay. So, innovations in in incremental levels are happening everywhere. Okay. Energy storage, for example, if I take another one, so that is not waste heat recovery that way, but something that we used or that we studied as part of this course. I mean, if you look at the amount of battery chemistry that people are working on today, it is just mind boggling. Okay. Lithium ion is something we know, but then there is redox flow, then there is a whole bunch of technology. So, for example, last summer I had gone to University of Waterloo for a short summer stint as a visiting assignment, and I had the fortune to meet a very leading researcher in battery chemistry. And what we found was, I mean, the gamut of things that she is working on was just, I mean, it was an eye opener for me. Okay. So, yes, I mean there are a lot of innovations that are going on. Fuel cells is another one. I mean, we saw the different types of fuel cells, but even within that, how do we come up with better designs? I mean, there is no end to that. Okay. So, there is a lot of scope for innovation at every stage and on every technology that we have discussed as part of this course, including flywheels, by the way, more on the material side. Latent heat, can you explain? Okay. Latent heat is the amount of energy, thermal energy that you have to supply when a substance is changing phase. So, for example, so during that what happens? The latent heat is the temperature of the substance does not change, but it changes its phase from either solid to liquid or liquid to gas. For example, if you are boiling water, and let us assume atmospheric conditions, standard 1 atmosphere pressure, the water is going to heat up till 100 degrees, and after that if you measure the temperature, ideally it should remain at 100 degrees. It is probably going to be slightly higher because you need a bit of superheat practically, but it is going to more or less stay around 100 degrees, and what you will see is the steam coming out and the volume of water in your pan going down. When you take out ice and put it in a glass and then put a thermocouple inside, you will first see that the temperature rises, and then once it reaches 0 and assuming absolutely ideally atmospheric pressure, you will see that the temperature is going to rise, then going to remain flat and then go up. So, then the question is that if the temperature does not change, is there any heat rejection or heat addition or heat absorption? Yes, it is, and the heat absorption is going towards changing its phase, either from solid to liquid, which is ice to water, or liquid to vapor, which is water to steam. So, this is latent heat. So, latent heat we discussed in terms of phase change, materials. So, phase change material or a PCM, when it melts, it remains at the same temperature, but it is absorbing heat. Okay. So, if I put a phase change material, so what happens is as it absorbs heat beyond and it starts melting, it does not let the temperature go any further up. Okay. And similarly, when it rejects heat, again it maintains the temperature, and so therefore, the amount of heat that is rejected when it is solidified can be used for room heating, or during a summer month the amount of heat that is absorbed can be used for keeping the room cool. Okay. Wow, there is a lot of questions have come in the last few minutes. What are the characteristics of fluid to be considered to be used in a heat pipe? It should have high latent heat, it should have low viscosity, high thermal conductivity. Now, these are all idealized situations, okay? None of these come together. So, these are some of the so good thermophysical properties, and to be frank, water is one of the best fluids that way. Okay. But what is also important is what is the temperature that you are trying to maintain it at. So, if you want the boiling to happen at 70 degrees, you have to choose a fluid that boils at 70 degrees, or evacuate, or if you have to use water, you have to use it in evacuated condition, okay, such that maybe the pressure has to be 0.3 atmospheres, so that the water boils at 70 degrees. Okay. So, these are some of the conditions that you have to keep in mind. Explain equipments which are used to convert low grade energy into high grade energy. So, I think that has been covered. Heat pump is one of the major ones. Okay. So, heat pump again is refrigeration cycle primarily, and it so the equipments used there will be a compressor, an expansion valve, and heat exchangers, and of course, there are lots of controls and all otherwise. Energy balance for evaporation, I think I just said that. So, the heat input should be equal to mass. So, Q is going to be mass times the latent heat, HFG, latent heat of vaporization. So, that is the heat balance. Evaporation in a container at a temperature. Oh, okay, for evaporation in a container at a temperature. Yeah, I think that is what it is. So, let us say if I take a jar of water and I put in some heat, and I want the entire water to boil off, then this is what it is. Are there any sources of untapped energy for usage like lighting up a torch with body heat? Wow. Not that I know of. Always keep in mind, however, one thing, that waste heat recovery, whatever we say, finally you have to use the Carnot efficiency, which is delta T or sorry 1 minus T c over T h. Okay. So, this has to be kept in mind. So, now if you want to use body heat, how much is body heat? Body heat, for example, so for body heat, eta of Carnot is going to be, let us say our body is at 40 degrees centigrade, okay, and 37 ideally, and then where are you going to reject it? You are going to reject it to the atmosphere, which probably is at 25 degrees centigrade. So, 25 is 298 and 37 if we consider, that is 310. Okay. So, what I am looking at is a difference of 12 degrees. Okay. So, this is very low. So, of course, ideally, theoretically, yes, you can probably use some kind of a heat pump or heat engine to get some work out of this temperature difference, but is this efficiency worth it, is the question. Okay. A similar question that people ask is, the hot air that comes out of your TV or a laptop computer or a desktop, is it can you use it? See, there also again the temperature of that air is around 70 degrees or 80 degrees centigrade. Your ambient is at 25, not worth it, okay, because the Carnot efficiency itself will be very, very low. Okay. And after that, Carnot efficiency is never attainable, you will never attain Carnot efficiency. You are going to probably, if you are very lucky, you can probably get to practically 60 to 70% of that. So, then you have to ask is whether it is worth it, yes. Okay. Next question. Are polymer electrolyte membrane PEM fuel cell and proton exchange membrane fuel cell both are same or not? Yeah. So, proton one you are talking about polymer electrolyte membrane fuel cell. So, that talks about the material of the membrane. Proton exchanges, because is the mechanism by which it happens. Okay. So, PEM fuel cell actually I think it is sometimes used by both ways, but PEM typically we use proton exchange membrane. Okay. Are you offering any other course in January to April semester in NPTEL? Yeah, that is completely different from what is what I taught here. It is called electronic packaging and manufacturing. Okay. I do not want to use this time, we have only 5 minutes left. So, I do not want to use this time to talk about electronic packaging and manufacturing, but I believe that the course introduction will come up in NPTEL. So, if it is of interest to you, please look it up. Okay. How can we contact if any questions later? The forum I think is the best way, it is being regularly monitored by our TAs and who bring it to the notice of me and Professor P.K. Das. So, I think that is the best way to do that. Introduce new course based on power plant installation. Okay, thank you very much, we will consider that. I do not know how much, whether I am really competent enough to offer that course. I do have some knowledge, but okay, I will definitely consider. Can we recover waste heat from sludge recovered from industrial wastewater? If it is at a if it is at an appreciably high temperature, you can again go back to this definition and make the judgment yourself. Do this quick back of the envelope calculation and say that what is the Carnot efficiency. Okay. If the Carnot efficiency is turning out to be like 10% or so, probably not worth it. Okay. But if the Carnot efficiency is turning out to be like 40-50%, yes, go ahead, because practically if your Carnot efficiency is 50% or so, then practically probably you can get reality in real life, you can probably get a 30% engine, 30% efficient engine. Different methods are used for waste heat recovery, but why waste heat is fully recovered? Probably you went why waste heat is not fully recovered. Again, I think all of it again can be attributed to this Carnot efficiency thing. Okay. Waste heat cannot be fully recovered because your final recovery, which is in the form of energy, if it is in the form of work energy, is limited by this Carnot efficiency. Okay. There will be losses if there is a temperature difference, there will be losses, second law of thermodynamics, we cannot help it, it is a natural phenomenon. So, waste heat can never be fully recovered, but we can try our best to recover as much as possible. Okay. I think, thank you very much, very interesting questions. It started a little quiet, but I think it picked up, the questions picked up as we went through. I hope I was able to answer many of your questions to your satisfaction, and again if I was unable, please feel free to raise these questions again on the forum. Once again, it was wonderful having you. We enjoyed the questions on the forum. I hope you also found this course worthwhile and learnt one or two new things. And once again, all the best on your exams. Don't be too stressed about it, and hopefully our paths will cross again in future. Thank you very much and have a very good day and the rest of the week. Bye.